My dear students, in this lecture we shall talk about the boundary layers. We shall discuss what is the importance of the boundary layer, how this concept came into being, and what are the possible areas where this concept can be used for getting the answers. We shall discuss about the displacement thickness, momentum thickness, boundary layer separation, etc. Now in this slide we are seeing that we have these two equations. This is the equation number 1, which is based on continuity equation basically for two-dimensional flow. Del U over del x plus del V over del y is equal to 0. This is the continuity equation for two-dimensional flow. Then this is the Navier-Stokes equation for two-dimensional flow, where we have simplified it by neglecting the del 2u over del x square, because in this equation it was having less value, that is why it was neglected. This is the NS equation, means Navier-Stokes equation for two-dimensional flow by having a suitable assumptions, by which we neglected the terms which are having less significance in this equation. So on left hand side of the equation, if we have a steady flow, then these are the terms related to acceleration. So mass into acceleration, these are the force basically, mass into acceleration term, and these are the body force and surface forces due to the pressure force and viscosity. So this equation is u del u over del x plus v del u over del y is equal to minus 1 over rho dp over dx. This is the pressure force due to the difference in pressure, and this is the force due to viscosity. This is nu kinematic viscosity del 2u over del y square. Now we can solve these two equations and we can give answer to question like what is the drag on a flat plate if a plate is kept stationary in any moving fluid. Like we have this situation, we have a flow taking place in x direction and we have kept a flat plate, right. On this flat plate we want to know what is the force being applied by this fluid which is coming with velocity u to hold this stationary in x direction. We have to apply the force in this direction to keep this plate stationary. So how much force needs to be applied on this flat plate to keep it in static condition? This can be answered by solving these two equations, but during the 19th century it was not possible to solve with the help of the so called mathematical equations prevailing at that time. So in 1904 Prandtl, he was German scientist, he studied and gave the concept of the boundary layer. So according to this concept, what he did, he divided the flow over a flat plate. This is a flat plate in which we have a fluid flow coming towards the plate with velocity v. He divided the flow near the boundary into two regions with the help of this dashed line. This dashed line is known as a boundary layer, this line is known as a boundary layer. So basically boundary layer divides the flow into two regions. This is region number 1, this is region number 2, shown with the help of darkness. And boundary and region number 1 above the boundary layer, velocity may be assumed as v. Everywhere velocity is assumed to be v. It is true also experimentally. So outer flow may be considered as a irrotational flow. Irrotational flow, it can be considered because outside the boundary layer du over dy is 0, because du there is no variation in velocity in y direction, so du is 0, so du over dy is 0. It means if it is multiplied by mu, this is also 0. So outer flow may be assumed as having no viscosity. This mu is like 0, though it is a fluid having some viscosity, but outside the boundary layer fluid may be assumed as a inviscid fluid or irrotational flow. Now irrotational flow can be solved very easily with the level of mathematics developed at that time, but inside the boundary layer the flow is a two-dimensional flow. Outside the boundary layer this is a one-dimensional flow. This was the one-dimensional flow, and here we have a velocity v which is in the x direction. Now inside the boundary layer this flow becomes two-dimensional because of this reason, to satisfy no slip condition. For satisfying no slip condition, what should be the velocity at this point at the solid surface? It must be 0, and as we move upward in transverse direction, then somewhere the velocity becomes 99% of free stream velocity, 99% of free stream velocity v. So here if velocity becomes 99% of free stream velocity, then this distance travelled in transverse direction, this is delta x because it is function of x. So at different value of x we have different value of thickness. This is defined as a boundary layer thickness, this delta is defined as a boundary layer thickness, and this is function of x, because at x is equal to 0 its value is almost 0, and as x goes up its value also goes up. So at this section of x, right, so what is delta? Delta is a boundary layer thickness at a given section. If we travel in a transverse direction, then velocity varies. Here at delta is equal to 0, velocity is 0 to satisfy no slip condition, and as we move upward the velocity increases and it becomes 99% of free stream velocity. So distance travelled in a transverse direction from 0 velocity to 99% of free stream velocity is known as a boundary layer thickness at that location. So this is the concept of the boundary layer which was given by Prandtl.